So in today's lecture, we are just simply taking uh, taking the data structure and all this like adventures thing. So we come with this recurrent topic, one of the important one. So this one is like most important. So before going to another topic, okay. So first of all, we understand some recursion problem. So and then move to the permutation problem, then combination problem, then subset problem, then the path on grid. So first of all, you know what is a recursion and what is this, but you have to see what's the perspective from my side and what are the questions we are expecting from this recursion series. Okay. So first of all, the who are the new in this like lecture. So who are the new in this lecture? So let me introduce something about. So by simply saying that rule number zero. Okay. Rule number zero is that if you know the recursion, just forgot the recursion. Okay. Okay. Forgot the recursion and uh, let's see what is like what I am studying, like what I am trying to teach you. Okay. So first thing, there are only function there are only function waiting for the smaller version of the same problem. So it's simply saying that like this is like a function. So this is called as a function, and he is waiting for the smaller function. Okay. So if we expecting the answer from this one, like we are expecting from the output from this like function, this function. So first function, and this first function is waiting from the second function. Okay. And this second function is waiting for the third function. Okay. These are this one is bigger than smaller and smaller. Okay. So instead of thinking, so like that's mean that I am calling myself. So I am right now, and this week I am recalling my previous like remember the things that I remember in previous thing. Okay. Someone else will solve the smaller problem. So like this one said that to solve the problem, this two said to solve this problem to three. Okay. The only one sentence change everything, that is calling itself. Okay. So if you like see this type of thing like calling itself situation, so this is a situation of recursion. Okay. And let's move to so next thing is the mental model one. Okay. Mental model one. So in this we have to see the human ladder. Just imagine just we have a ladder. Okay. A ladder of 100 steps. Okay. 100 floor, yeah, 100 step floor. Okay. So if you don't jump to the directly from the like if you are like at the top, this is the building. Okay. So this is the building, and if you put a ladder on this one and you are standing in this place, you don't jump directly, like you don't jump directly to the ground. Okay. So in that case, you ask the person below, like another person is like here, and another person is here, and another person is here. Okay. You say like you can say another person, you ask the person below you. He asks the person. So you asks this person to please go one step down. So he asks one step. He asks this person to go one step down, and he asks go one step down. Okay. So answer is then answer travel back to the upward direction. Okay. So if this guy added a last position, just leave the list ladder. So simply this go down, and this go down. Okay. So this is what actually recursion solve. So in recursion, we can say that we can say that if I want to solve something at the 100 position, so I say to solve the problem by 99. I am the 100 guy, I have some problem. So I give this problem to the 99th guy, and 99th guy or say like solve the problem and say that to 98. So again, go, and finally we stop at the stop and return the answer. Okay, then we return the answer. Okay, so this is what a recursion. So the downward journey is asking. So you can see here. So you can see here. So this step is like asking for the asking for availability, as asking for the answer. Okay, asking for the answer, and this is journey for like giving the answer. This is the two-way direction. Okay, so most student only understand the downward part. So like most of the student only understand this part, like downward path. So you think that solve this problem, this, but he forgot about this upward part, that the answer part. Okay. Okay. And so let's see one more golden formula. So like I'm writing here the I'm writing the golden formula for the recursion. So golden formula of the recursion. So golden formula of the recursion, just we have some function that is int solve. Okay. Inside this one we have some like some values int 10, and if I want to solve, so I will tell him that you have to first of all think about the base case when this stops. Okay, then I ask him for the trust recursion. So trust recursion, what he trying to solve, and third one is that use your answer, like use it answer. Okay, this is all about recursion's golden formula. This is that everything else is a decoration. So you have to simply you have to focus on three these golden formulas. Okay, and this like so okay, let's see one example that is like the basic or generic example you have already seen, that is like if you want to find the factorial of 5, so what you have to do. So I tell the best case is that if when the like we reach to the 1, stop it and trust the recursion. So this look like 5, then 4, then 3, then 2, and then 1, and we reach to the 1 and then stop and give the answer. Okay, okay. So this is whole thing about the recursion. Okay, so it's simply like I am writing 5 into factorial of 4. Okay, if I got the answer like 5 into 4, so that I have to write the factorial of 3. So like this one. Okay, so the sample code for this one, it's look like we are like writing integer factorial of 5. Okay, so int 5. Okay, so we have integer n. Okay, and we are finding it. So in that case, if our n value is become 0, so in that case we have to return 1. Okay, otherwise we have to return and search for the like smaller of like one step down. So in that case factorial n minus 1. Okay, so this is the code, and like this is the code what you have to trust. Okay, and we never compute, so I only compute 5, we never compute 4 factorial. Okay, we simply trust the recursion. And same as like we are finding for if you want factorial factorial of 100. So in that case, we are just asking factorial of 100, but we don't know how to like find the factorial of 99, 98. Okay, just this recursion will be held in this case. Okay, if someone asks to give me a factorial of 90, like 99 factorial, so how I can produce 100? So this is the process. Okay, and if you want a sum of the array, so how can I find? So if I like if a person, so like someone asked me to find the, let's see, so if someone asks me to like give a sum of array, like sum of array, so a sum of array means like we have like 1 2 3 4 and 5. This is the array. So how I write this code? So in that case, we have this integer box inside, integer sum, in which like integer sum, and in which we have a vector inside. All this thing is written, so I can write as a, and where I have to start from the 0th index. So yeah, ith index. Okay. Okay. So in that case, first of all, if I reach to the a dot size at the end of this this array size, so in that case we have to return 0. Okay, the time when we have to stop, this is the base case. Otherwise what we have to do, we have to return what we have to return. So first of all, a of I plus, then we again call this function once again, sum it remains same, vector remains same, we just do the one step forward. Okay, and this is the whole this by writing this one, we move to the, like we are simply multiplying 1, then some 2 for the rest, a of like 1 index, so 1 plus 2, then again some 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4 again, and finally we reach to the end of, so it will return what we have. So it will return like answer 15. Okay, so this is what the recursion, all the things about the recursion. Okay, so we have to set a pause, like a pause for all the, so every recursive call presses pauses. Okay, so if we are writing solve 5, so it take pause. Okay, and then it solve for the 4, and then take pause. Okay, so nothing above run until the below is finished. Okay, the compile literally store where to return variable, current value, and current line. Okay, so like you are like, imagine you are watching a movie and every recursive like function pauses, start movie, that movie pause, start another movie, eventually one movie finishes and everyone resume it. Okay, so like whenever the 3 question, the like, so let's see one more thing. Okay. So okay. So like 3 question, like 3 golden rule. The 3 questions. The 3 question we have to think, or 3 questions. The first question is that what is changing? Okay, so what is changing? What is changing? Okay, so the answer for this question is this question is that, okay, so like we are changing this n, this index. Okay, node is changing, and string is changing. Okay, pointer are changing. Okay, so these are the thing are changing. Move to the next question. Move to the next question. Next question is that when should I stop? Like when should I stop? So you have to set some base cases. You have to set some base case when you have to stop. Okay. And the third question is that how can I reduce the problem? Okay. So if you are at the n, so we have to reduce this problem by n minus 1. If you are at the index, so we have to reduce to idx minus 1. If you are at the node, so like a node, where a particular node, so either you can go to like a left child, okay, or you can go to right child and side of right child, okay. And if you are at a pointer, so you are like string on, you can go to the some string, okay. So these are the how can I reduce the problem, okay. So like 4 type of recursion I have to learn. So one recursion is like factorial sum power GCD, and second is linear recursion, okay, like print 1 to n, like n to 1, reverse the palindrome. Third type is like Fibonacci subset, permutation, and queen. And then move to the backtracking, okay. So like the term is like the term is like backtracking. So the backtracking. What is this backtracking? So like you are like so first of all, just imagine you have 3 houses, okay, 1, 2, and 3, okay, and you have to ask like in this Ramesh live, okay, Ganesh live, and Suresh live, okay, and I am the person, I send you and ask where Ramesh is living, okay. So I go to this place and ask Ramesh is living or not, and I have to inform that Ramesh is not living on this room. So like, so he said that go to another room. So okay. So go like not backtracking mean that go to this room now, okay, and see if it like Suresh is living. No, so it came back and again explore for this one. So like so what are the 3 things you can see this from the arrow? So this arrow is like this arrow indicate do, explore, and undo, okay. Yeah, you can say that do, undo, explore. So you are doing, you are going, so this means you are doing something and you are coming back, it's like you are undoing your step, okay, and you are exploring, so you are going to in this direction, so you are exploring. So this is all about, this is all about the backtracking thing, okay. What is backtracking? So if you like do, explore, and like do, undo, and explore, the biggest mistake everyone they trace like recursion in a line. So don't think at the higher level what happened next. If a smaller problem is solved, then what should do next, okay. So you have to like go like whenever like why it is more important, because interviewer don't evaluate whether you know the recursion or not, okay. So it's simply like they evaluate whether you define the state or not. So like defining the recursion, so like defining the state is more important, okay. So defining the state is more important as like solving the problem. For example, if you write like DFS and in which you pass the node, okay. So you know how, why, and how I like write this in what does the function promises. So what this like function promise, okay, what this function promises to like return, okay. I want to know. The next question is like return the height. Like if you I like it, this one, so it will return height, like diameter, yeah, maximum path, or we can say sum. So what is this? So this have to be explained clearly. The functions should have only one clear responsibility. So I don't expect, like I am not expecting that this like a simple function returns sum, comma, like height, okay, like diameter, okay. I am expecting one single responsibility, okay, single responsibility from this function, okay. And just like first of all, I know that you know all this basics about the recursion. So you know how to print, let's print one to n. Okay. So you know how to print one to n. So you can, and again like n to one. Okay. Just simply print the current number n. Okay. Then move to the next solve function and move to index I plus one. Okay. This is all about sum of factorial, reverse, check polynomial, like binary search, all this thing, and then move to like subset problem, rat maze, generate parenthesis, okay, generate parenthesis, combination sum. All these are the like problem based on the recursion. Okay, so whenever you write a recursive function, write these three functions first. What is the smaller? So whenever you are writing the recursive function, so like whenever you are like writing the problem, so first of all, the first thing you have to write what is the smaller problem. Okay, so think about the smaller problem, what we can make. Okay, second thing is what is the base cases. Base case is more important when you have to stop this thing, base case. And the third thing is that how do I use this smaller answer. Okay, okay, how I use this smaller answer, use this smaller answer. So this is also important. Like you have to like focus on these three things, like smaller problem and base cases, and how can I use this smaller answer. Okay. So if you can answer only three questions, then you can solve a vast majority of the recursion problem. Okay. So foundation is like important. Okay. So like foundation, foundation of recursion is important. Then recursion on array. So first of all, you can apply this recursion, recursion on array, then string. So you have to like use to string, and then binary recursion and the recursive tree, or the binary recursion or the recursive tree, and then move to the topic that is backtracking and the advanced like entry question on this thing. Okay, so let's solve some problem. Like let's solve the problem. So recursion problem. Let's see one. To solve the problem that is I am using a problem that is simple. This problem was this one is a big. Okay. This is all about the problem. So let's see. This problem is like solve like two sorted list. Okay, two sorted list. So you are given a like two sorted lists, that is list one and list two. Okay, and when the two lists are like two lists into one sorted list, so I have to like return into a single list. Okay, and list should be like splicing together, and the node of the list like a node of the first list, the first two lists return the head of the merged list. Okay, so like, you understand the problem? So we have the two sorted list. So we are having this two sorted list. Like, okay. So we have two like list. Okay, so in this like one is there, like two is sorted. Okay, how can I do? So what we think about this one? What are the thinking? We have to first of all, this is the list. So like like the first thing that come in my mind, like in this list, like we have one, two, and four. Okay, and this list also have like one, three, and four. So we can see here, like this also having like one here, okay, and one here. So which list like number is like given first? Okay, the first thinking like come in my mind is that first of all we use two pointer, left pointer and the right pointer. But uh, this is a linked list. Okay, so first of all this is the linked list, and linked list. In this like you have like traversing through the left pointer and traversing through the right pointer. So in that case, and we also have to create a link list. So our answer is also a linked list. So okay. So how can we process this question? So like, solving this like, so think for the like thinking for the approach for the like only 10 minutes. All just like thinking. So think think brute forcefully. Okay, and then we are trying to optimize. Okay, so in this like input in the form of list. Okay, so input form and the list. What we have to do? I'm not trying to code, just simply do this thing. Okay, so like left pointer. So this left pointer on this one, and this having the right pointer. Okay, so while so this right pointer when L is not is equal to null, null in that case, and like, so you can say that this question is like merge sorted array. We have the we have seen like merge sorted array, but this is like merge sorted linked list. Okay, so this is like kind of similar as from my side. This looks similar. So what is the approach for this one? Just imagine, just we are thinking about it like merge, like sorted array. In this case, we have 1, 2, 3, 6, 7, 8, and this one. Another list we have like 2, 2, 5, 8. Okay. So in that case, we are using a left pointer and we having the right pointer. Okay. We run this loop. Okay. So first of all, we are checking this left or right. So in that case, who like which one is like bigger one. So if like array of L is smaller than array of R side, so in that case our answer this box. So we have this box. Okay, the box like this value. Okay, so in this box we are filling this value. So just imagine we are at this position. So this one is less smaller than this one. So we are putting the one value here, and we move this left pointer to this position. Okay, left plus plus, and we are comparing. So if right is smaller, so in that case we put the right again, move to this position right. Okay, and again we are checking. Again we are checking which one is smaller. We are seeing that 5 is smaller, so we put inside this box and we are moving this right pointer here. Okay, and at this position 6 is like smaller, put here. Okay, and this one like left position again checking 7. Okay, and this is like over, so we can't go like here outside this one. So again 8 is left here only. So how can we, if any of this like array is not like completely filled, in that case we have to run like while we have to check the condition for this one. We have put all this value. So if it is not empty, if it is not empty, okay, not empty, so in that case we put the value to here. Okay, so let me like write the code for the like merge to sorted array. Writing the code for the merge of sorted array, and they also understand the time complexity. So we are trying like covering this whole size. This is like m size. This is also like n size. So we are covering. So that's why the order time complexity is order of n plus n. Okay, and the space complexity. So we are filling all this value. So like size of this, size of this one, and the space complexity is like order of n plus n. Okay. So what is the first approach like come in our mind? So these are the first approach. So if you are like merging the array, so in this like we have to like vector merge sorted array. So in which we have a vector of array 1. So we are like here with the vector of like okay, vector of integer in like name is like array 1, and another is like array 2, and we have another array 2. Okay, we simply like use two pointer as we discussed earlier. Int I is equal to So we are using to pointer at li is equal to 0 and j is equal to 0. Okay, and we are using while loop to run this one. So till I is less than what? I is less than array one dot size. So this one is written as array one dot size. Okay, size and j will move to the array two dot size. Okay, so this is clear and this is clear. So after that, after that we are just checking. It's checking if this I side is greater. So okay, if array of one of I is greater than this array of j, so in that case I put answer push back that element and I plus plus. Okay, so if case, okay, and else case is like simply answer dot push back array of 2 j and j plus plus. Okay, so after this while loop all the thing is like filled. Okay, so what will adding the remaining element? So for that one case, like we are like while loop, this is I less than array one dot size. So if it is not full, so just push that value, push back the value of array of I. Similarly for the till j is equal to array 2 dot size thing. Okay, and return the answer. Case of now we have to check in the case of linked list. Linked list. Okay, so what if like two sorted array? So now we move to the our question, that is like linked list. We understand what is like what is sorted array. So now we have to see this question merge to sorted list. So in that case we have to think. Okay, so what we have to do? Merge this one. We have list one and list two. Okay, so we have two list node, that is list one and list two. Let's where we have right side. Okay, let's try to write here. Okay, so this side. So what we have to do? So first of all I have to like, this is like simply we have list node and list node and we want to merge this. Okay, and we have to like list node that is like from list one. So we simply write as a L1. This is L1. Okay, and second is like, okay, and second is like node star L2 list 2. So first of all what I have to like what I have to see, first of all, if list 1 is equal to null, so in that case we have to return L2. Okay, similarly if our L2 is equal to null, base case is important, then return L1. So like we so like let me change the color channel to okay. So in that case we are seeing that this is our base case. Base case, we write the base case and we move to the next part, the movement or traversing part. Okay, so what is the movement and traversing part? So first of all I have to write the code. If condition, if like list one data, list one data is less than is equal to list to data. We have to check. So in that case, we have to write in it, call the merge sort. So L1 dot next is equal to merge, and just like we are calling the same function merge, and in that case we are like initializing the L1 dot next, and this L2 remains same. Okay. Okay. And finally we have to return the L1. Else case we have like, else case if like this is not correct, so in that case L2 dot next is equal to merge, and L2 dot on this remain L1, okay, comma this will be L2 dot next, okay, and then finally we have to return L2, and this is clear. Okay, so this is the whole code. So let's see how the code look like. So we have try run this thing. Okay, so we have 1 3 5, and this is like 2 4 6. Okay, so first of all we are at this position. First of all we are checking this thing, so which one is greater. So we are checking L2 is greater this one. So in that case I return 1 plus merge solution of this one, and we move to 3. In this we have this node 3 to 5, and in this we have to go 2 to 4 to 6. Okay, and return again. Now we have to check, we have 1. Now we have to check, compare between 3 and 2. Okay, 3 and 2. Okay, which one is greater? 2. So we can write 2 plus merge, and we have 3 5. Okay, 3 5, and now it will be 4 6. Okay, and now move to the next part, and now we are comparing. So this, we are at this position, we are comparing with the 4. So in that case 3 merge, we have left with the 5, and this will remain 4 and 6. Okay, now we are moved to this position 5 and comparing with this 4. Okay, so in that case we can write 4 merge, 5 left, and this 6 left. Okay, and move to the next part. Okay, now we are comparing. So in that case we have to write 5, then merge, and this remain, this become null. Okay, this become null because we move to the next part, and this remains same 6. And finally if any of this become null, so we simply return the another node that is return 6, as we as we discuss here. So as we discuss, if any of this value get null, so in that case we have to return. Okay, so this one is the dry code, and no recursion unwind. So it look like after 1 we put 2, after 2 we put 3, after 3 we put 4, after 4 we put 5, and finally we have to put 6. Okay, this is how the dry run code look like. Okay, and at every recursion call you can only decide which node come first. Okay, and trust the recursion process. So like it's solved by using the recursion. So first of all you have to trust the recursion. Okay, trust the recursion. Okay, if you know how to merge the smaller like a remaining list, you can merge the currently list by like choosing or like smaller head. Okay, and I earlier told that the time complexity is simply n plus m size, and the auxiliary space complexity space is like also m plus n. Okay, same due to the like recursion stack in the worst case scenario. Okay, so like completed. So in the next lecture we are trying to solve more question. Okay, and understand all the dry run inside the code. Okay, thank you.